Namaste children, welcome back again to this virtual class. So in today's session we will be starting a new chapter, that is magnetic effect of electric current. And in the last episode we have completed the chapter electricity and we winded up with the heating effect of electric current, right? Hope you understood that. When we talk about heating effect, it is the electric charges when flow in an electric circuit, then heat is dissipated, right? And we have also seen about the Joules law of heating, H is equal to I square RT, which means in an electric circuit when electric charges flow, then heat is produced. The amount of heat produced in an electric circuit is directly proportional to square of the current, directly proportional to resistance and directly proportional to time. Which means if current is doubled, then the heat produced in the circuit will be 4 times. We know that the square of 2 is 4, so 4 times the heat energy will be produced. And also if resistance of the circuit is increased, then also the amount of heat produced will be more, which we will see in electric iron and all. And also if time is increased, that means if a bulb is operated for 1 minute, then you will feel some warmness. If the same bulb is operated for 1 hour or 2 hours, then you can see very well that the bulb gets heated up at a much larger rate. So this way we can understand what is the heating effect. So altogether we should understand that whenever electric charges flow in an electric circuit, then heat is dissipated, heat is liberated due to the resistance, time and the flow of current. So this is one of the effect which we have seen and completed in the chapter electricity. So in today's session we will be seeing another effect of electric current, that is magnetic effect of electric current. When electric charges flow in an electric circuit, heat is produced. Along with this, magnetic field is also produced. About that only we will be seeing throughout this chapter. When magnetic compass, you are much familiar with magnetic compass. I will show you the magnetic compass. So here is the magnetic compass. The main purpose of this magnetic compass is to find the direction, right? By using this we can find the direction, which direction is north, south, east and west. When this magnetic compass is brought near the current carrying conductor, then you will find that the needle of the magnetic compass deflects. Under normal condition, the needle of this magnetic compass aligns itself in the direction of north-south. We know that Earth is considered to be a large magnet which contains north and south pole. And here in this compass we see 2 directions, right? One is north direction and another one is south direction. The needle which points towards the north pole of the Earth is called the north seeking pole, or simply we call it as north pole. Similarly, the other end which is pointed towards the south pole of the Earth is called south seeking pole or south pole. Under normal condition we won't see the deflection of the needle. When the same compass is brought near the current carrying conductor, then we could see some sort of deflection of the needle, and this deflection is observed only if the magnetic field produced is greater than the magnetic field produced by the Earth. So we can say that when the magnetic compass is brought near the current carrying conductor, the current carrying conductor also produces magnetic field, and which is greater than the magnetic field exerted by the Earth. And let us understand some of the properties of magnetic field so that you will understand this chapter in a better way. When we talk about magnet, you must have studied in the lower classes as well. So let us recall some of the properties which will help us to understand the remaining portion of this chapter. So when we talk about the magnet, there are some important characteristics that has to be understood. The first thing is, magnet has 2 poles, one is north pole and south pole. Just before we have discussed the needle of the compass which is directed towards the north pole of the Earth is called the north seeking pole or north pole, and the needle which is directed towards the south pole of the Earth we call it as south pole. So every magnet has 2 poles. So here is a bar magnet. Here you can see very well, one is north pole and another one is south pole. If you cut into 2 halves, then how many poles you will see? 4 poles, 2 north poles and 2 south poles. No children, if it is cut into 2 halves, then each piece will acquire once again north pole and south pole. So this way we cannot separate the poles. So we can understand that every piece of a magnet have 2 poles, that is north pole and south pole. The second important characteristic of magnet is like poles repel each other and unlike poles attract each other. Now we have two bar magnets. You can see very well, here it is the south pole and here it is north pole. Here I am having two bar magnets, here north pole and here also north pole. When I bring the north pole to one another, then you can see very well that they are getting repelled each other, right? So, and if I bring both the south poles together, then you can see very well that here attraction we could not see. We are not seeing any kind of, instead it repels, right? So you can see very well that they are repelling. So like poles repel each other, and if I bring the unlike poles means north pole south pole or south pole north pole in opposite combination. Here is a south pole and here I am having north pole. If I bring north pole towards south pole, you can see that they are attracting. So this is one of the most important characteristic of magnet, that is like poles repel each other and unlike poles attract each other. When I suspend this bar magnet freely in air, then what will happen? Earth is considered to be a large magnet which has north pole and south pole. When I suspend this bar magnet freely in air, after some time they align itself in the direction of north and south. So this is also one of the important characteristic. So based on this, we try to understand, we go into this chapter now. We know that magnet exerts a force of attraction with which magnetic substances like iron gets attracted towards itself. Now you see on the screen here a bar magnet and some iron filings are spreaded. Upon tapping on the surface, you can see very well that a pattern is formed to a certain region. From this we can understand that the bar magnet exerts some force with which the iron filings are attracted and a pattern is visible, right? Now from this we try to understand what is magnetic field and magnetic field lines. Now you can see on the screen that the pattern is visible to certain region. So from this we can understand that the influence of the magnetic force is to a certain region. Beyond that, its influence is not seen. So we can understand field, magnetic field, as the influence of magnetic force to a certain region around the magnet is called magnetic field, and the pattern what you are seeing is called magnetic field lines. And here line indicates that direction of magnetic field. The magnetic field lines what you are seeing on the screen has direction. So to know the direction of the magnetic field lines, we have an activity. From that activity you will be very much clear about the direction. Now we have a bar magnet. As you can see, this is the north pole of this magnet and this is the south pole of this magnet. Now the magnet exerts force around itself, we call it as magnetic field, and the magnetic field has some direction, we call it as magnetic field line. The magnetic force is extended to certain region, we call it as magnetic field, and we find out the direction of magnetic field lines by using a magnetic compass. Now I have a magnetic compass, as you can see here. To trace the path of the direction of magnetic field line, we make a region over here. So from here we will make a region. Over this line, let us keep the magnetic compass to find the direction. Now you see, when I kept the magnetic compass at the edge, you can see the direction, right? So this is the direction, we mark the direction. So after removing this, we can make the direction like this, right? So when I placed here, then you can see that the direction of magnetic field line is this, and when I keep here, then the magnetic compass needle deflects towards this direction. So we can mark here as like this. So as I keep continuously, then we will get here in this compass. You see the red line indicates the north pole. So here the red part is the north seeking pole. So the direction of magnetic field line is from north direction to south direction, right? Now if I keep the magnetic compass and pass over the magnet, then you can see very well that you see here the direction of the magnetic field is from south to north. It is observed that the direction of magnetic field lines outside the magnet is found to be originated from north pole and ends up at the south pole, whereas inside the magnet the direction is just opposite, that is the direction is from south pole to north pole. And the magnetic field lines can be represented by the picture as you can see on the screen, and in this picture you can see that the lines are crowded at the poles, which indicates that the strength of the magnetic field is more at the poles, whereas as the lines go away, as the distance increases, then you can find the distance between two lines, any of the two lines are more, which indicates that as the distance from the magnet increases, then the strength of the magnetic field decreases. From this we can understand that the magnetic field is inversely proportional to distance, which means if the distance is increased, then magnetic field is decreased. If the distance is decreased, then the magnetic field will be more. From this we can understand that magnetic field produced by the magnet is inversely proportional to distance. So now we are clear that when electric charges flow in an electric circuit, then magnetic field is produced. Now the question is, what will be the direction of magnetic field? In a bar magnet it is very easy because north pole is available and south pole is there. From this north pole to south pole the direction of magnetic field will be, but in case of a current carrying conductor, what will be the direction? To understand this, let us see here a simple electric circuit. Here the wire is on the north-south direction. Here what I am going to do is a magnetic compass is placed parallel and above the surface. Now when the electric circuit is put on, then the electric charges start flow from the north to south direction. In that case you can see very well that the picture shows the magnetic compass needle deflects towards east. Now if I reverse the flow of electric current, if the flow of electric current is reversed, in that case you see the magnetic compass needle deflects towards west. From this we can understand that the direction of the flow of electric current decides the direction of magnetic field. So on reversing, the direction of magnetic field also gets reversed. So there is a relationship between the direction of electric current and the direction of magnetic field. Now let us take one of the example. If the current carrying conductor is the straight one, then in that case what will be the direction of magnetic field? To know the direction of magnetic field in a straight conductor, straight current carrying conductor, we have a rule called right hand thumb rule. So what is that thumb rule? So let us take an example. Here I am having a straight conductor. Let us assume that this is a straight conductor and I am having right hand, so right thumb is also available. Let us understand to now how the direction of magnetic field could be found out. Hold the straight current carrying conductor this way. Here thumb indicates the direction of electric current and the fingers wrapping around the conductor is the direction of magnetic field. Then how can we understand this? Here you see the conductor, this is the direction of electric current and the direction of magnetic field will be this direction, right? So the fingers which are wrapping around the conductor, this way it is wrapping around, right? So this is the direction of magnetic field. If I invert the conductor, then in that case what will happen? Here you see the direction of electric current is towards downward direction. In that case the fingers are wrapping this direction. So this is the direction of magnetic field. So by using right hand thumb rule we can easily find the direction of magnetic field in a straight current carrying conductor. Understood, children? If the current carrying conductor is straight, then it is very easy to find the direction of magnetic field. By using right hand thumb rule we can find. If the conductor is in a circle or circular loop is there, then in that case what will be the direction of magnetic field? Now look at the screen. Here is an example of a conductor which is in circular shape, right? Here also the same rule will be applied, but the difference is as we move from one end to another, the direction, the position of our hand also changes. Now you can see on both the sides we can see two different directions. So this way the direction of magnetic field in a circular loop could be found out. A coil of many turns of insulated copper wires wrapped in the shape of a cylinder is called solenoid. Now the pattern of magnetic field lines you can see on the picture, which is very much similar to what we have seen in the case of bar magnet, right? Now here one side acts as a north pole and another one is south pole, and the magnetic field produced by the solenoid is very large. So we can say that the strength of the magnetic field is more in case of solenoid. Due to strong magnetic field produced by the solenoid, it can be used to magnetize magnetic materials such as iron, soft iron. When the soft iron is put inside the solenoid, it acts as a magnet. The magnet so formed is called electromagnet, since the magnet, it becomes magnet only when the electricity is passed. Based on this, it is used in various places. For example, in removing scrap irons, the cranes are fit with the electromagnet. When it needs to be detached, we have to stop the supply of electric current, so it is no more electromagnet. So this way scrap irons can be transported from one place to another by making use of electromagnet. Dear students, we have two circuits on either sides. In one, bulb is there and another one is fan. Let us suppose if we put on the switch, here the bulb glows but the fan does not glow, and here the fan rotates and here bulb does not rotate. What could be the reason? Here in both the case, what happens? The electric charges flow, right? Electric current flows. Due to the electrical energy, here bulb starts glowing, whereas here the fan starts working, rotating, right? Now suppose the electrical energy causes rotation of a fan, then why not the bulb gets rotated? Very interesting, right? Now to understand this, we have to see another important concept of magnetic effect of electric current. Dear students, when current carrying conductor is placed in a magnetic field, then there exists force. With that force, the blades of the fan gets rotated. Now here inside the fan you will find a motor. About that we will see later, but for now you just understand that whenever a current carrying conductor is placed in a magnetic field, then force will be exerted, right? Now we know that force can make the object move, so with that force the blades of the fan rotates. Now we have to understand, if current carrying conductor is placed in a magnetic field, force will be produced, then what will be the direction of the force? That we don't know. To know the direction of the force exerted by the current carrying conductor when it is placed in a magnetic field, we have another rule. By making use of that rule, we can easily find the direction of magnetic field, electric current and force. The law is called Fleming's left hand rule. So for that you have to do some finger exercises. What is that exercise? Here you have to extend 3 of your fingers in such a way that all the fingers make right angle to each other. To understand this, you can take the corners of your room. If you take the corners, you will see 3 different directions, right? So like that you can assume that 3 fingers are there and all the 3 fingers are right angle to each other. If you could arrange these fingers and understand, you can find the direction if you know any of the 2 quantities. Now to understand this, each finger is related to some quantities. Here thumb indicates motion, here central finger indicates the current, and forefinger indicates magnetic field. How can we remember? That has to be remembered. No, it is a very big task. Now to understand that, what you need to do is C, central finger, C for current, here forefinger F for field, that is magnetic field, here thumb. In thumb you can see M is focused, right? So M means motion. So by this way you can remember the short code of this. By knowing this you can easily find. Let us take some of the examples so that you will understand in a better way. In the textbook also some of the questions are given that you try to solve it. If you have any difficulty, then you can ask us very well. Now let us take an example. Now I am bombarding some electrons towards you. If electrons are in the direction of you and I am applying magnetic field, suppose magnetic field is above, so we have made right angle, right? So what will be the direction of motion? Now you align your fingers in such a way. Now I have told you that electrons are bombarded to your eyes or forehead, we can say. So the direction you can identify, right? So electrons are in your direction, but we have to talk about, we have to see the electric current. You should know the direction of electric current is opposite to the direction of flow of electrons. I have told you that electrons are coming towards you, then electric current, the direction of electric current would be towards my direction, right? So central finger indicates the current, so I have assigned here. So the central finger is aligned towards me, and what else I told? Magnetic field is in the direction of upward direction. So what is magnetic field? This is the magnetic field, right? So this is the magnetic field. So what will be the direction of motion? The direction of motion will be towards this direction. Got it, children? So this way you can find various other possibilities. You try in all directions. If you have any doubt, then you can contact us. So now we are very much clear that when a current carrying conductor is placed in a magnetic field, force is exerted. Based on this principle, various devices are developed and we are still using. Can you name one device? In the beginning, just before, we have talked about the electric fan. Inside the electric fan we have motors. So electric motor is one of such device which is based on the principle of what we are discussing now. Now let us understand how electric motor works.
Here is the diagram of an electric motor. Consists of a rectangular coil ABCD of insulated copper wire. The coil is placed between the two poles of a magnetic field, that is north pole and south pole. The coil is placed in such a way that the arms AB and arm CD are placed perpendicular to the direction of the magnetic field, that is between the two magnets. Here you will find the split ring. The ends of the coil are connected to the halves of the split ring. The inner side of these halves are insulated and attached to the axle, as you can see here. The external conducting edges, that is two conducting stationary brushes X and Y. When you put on the switch, the electric current starts flowing from this direction and it enters into the coil from AB and comes back from CD, and accordingly the circuit gets completed. Now let us see how the motor works. Now when the key is put on, then the current flows from this direction, and in the coil the current enters initially through the direction of AB. Let us now apply Fleming's left hand rule to find the direction of motion of this coil. Here the direction of magnetic field is towards north to south direction, right? Now we have to align the first three fingers, that is thumb, forefinger and center finger, in such a way that the forefinger points towards the direction of magnetic field, that is this direction, right? Now electric current is towards this direction. So the direction of electric current is this direction, here right angle to each other, right? Now what will be the direction of motion of the coil? If you extend, you try yourself, when you extend this way, then naturally the third finger, that is the thumb, will point towards the downward direction, which means here it is direction of electric current and this is the direction of magnetic field. If you align your three fingers, then the third finger will point towards the downward direction. This will be the motion. If we made such an arrangement on supplying electric current, when the electric current flows through the coil at the arm AB, then the direction of motion of the coil will be downward direction, right? So at this point what happens, the coil will be pushed downward direction. When the current reaches the arm CD, in this case what happens about that we will see. Here also we will apply once again the Fleming's left hand rule. Here the direction of magnetic field is same, that is this direction, but here you see the direction of electric current is opposite to the direction of electric current which flowed through the arm AB. Through AB the direction is this direction, right? Whereas when the current flows through CD, then the direction of electric current is this direction. So here it is magnetic field, we can write here, and this is the direction of electric current. Now once again you align your three fingers according to Fleming's left hand rule. Then in this case you will see your thumb is pointing upward direction, right? So here your thumb is pointing upward direction, so this will be the motion of the coil. When the current enters through the arm AB, then the coil will be pushed downward. At the same time, when the current enters the arm CD, the coil will be pushed upward. So at this point what happens, on half rotation AB goes down and CD is pushed upward. So both the way the force is applied on the coil. By using this force, what happens, the coil turns halfway. On half rotation what happens, seam comes this side, that means here C and B goes this side. So here will be B, and similarly D comes this side, so A, this arm will be D, and A goes this side, so here this will be A. Now you see, earlier when the current entered through CD, the direction was different, but now the totally on half rotation CD comes to left hand side and BA has gone to right hand side. Now you see the direction of electric current is from DC. Here by applying Fleming's left hand rule, the arm CD goes downward. In the earlier case, the arm BA was pushed downward whereas CD pushed upward. Now due to half rotation, the coil gets reversed, and here we can see the flow of electric current is reversed. Due to the reversing of the coil, the flow of electric current has also got reversed. Now in place of BA it is CD, and in place of CD it is BA. By applying Fleming's left hand rule, now you can see very well that the arm which is pointed towards the left hand side earlier pushed downward, so now in place of BA it is CD, so the CD arm will be pushed downward, and the arm CD becomes now BA, so the BA will be pushed upward. So once again half rotation takes place. So this way motor keeps on rotating continuously. A device that reverses the direction of flow of current through a circuit is called commutator. In this electric motor, the split ring acts as a commutator. You always keep in mind that such type of simple question, 1 mark question will be asked in the CBSE examination. Here the main role of split ring is to reverse the direction of flow of electric current, which acts as a commutator. So we can say that the reversing of the current is repeated at each half rotation, giving rise to a continuous rotation of the coil and to the axle. Understood, children? In commercial motors such as electric fan, which we were discussing before, an electromagnet is used in place of permanent magnet. Large number of turns of conducting wire in the current carrying coil is also used. A soft iron is placed on which the coil is wound. The soft iron core on which the coil is wound plus the coils is called an armature. Hope you understood the working of electric motor. This is very important as per your personal knowledge or as far as examination is concerned. You just understand the principles and the working and the diagram. Also you practice it many times, so you should have some grip on this. So that's all we have for today's session. With this I would like to conclude. Before concluding, I would like to give some easy home assignments which you can practice at home. Here is your home assignment. Hope you will do all these home assignments very easily. See you all on another day with new topic, that is induced current. Very interesting topic. Till then, keep learning. Take good care of yourself. Bye.